Okay, so we're going to run through a complete project again, and this one's going to be a bit more complicated. So it's actually going to be split up into 6 parts so far. It might have a 7th one. We're going to go all the way from collecting data to storing data and also communicating data between Arduinos. And we're going to use both regular RF radio frequency, and we're also going to use Wi-Fi. So let's get right into it. Okay, so let's begin with our project design. Okay, so let's pretend that we have a warehouse with some product. We've been hired by a client who has a warehouse full of valuable cash crops or some kind of product that he needs to keep tabs on. So let's say we want to measure things like temperature and humidity, or we could also measure UV light, which is very damaging. Or we could measure dust in case we don't want the environment to get too dusty. You don't want people getting sick, etc. Okay, so now let's pretend that we have an office building. So these are geographically or physically separated from one another. Could be short distance, could be long distance. Okay, so this is an office which is even a different environment. Maybe you want to measure the quality of air. So you need to send data from the warehouse in some kind of wireless form and receive it over at the office building. Maybe even combine it with the office building data. And there are sensors called MQ sensors which measure quality of air. And you want to do this using RF, radio frequency, and LR, RF, which is long-range radio frequency. Or the other option we could consider, obviously, is posting this data directly to the cloud. Okay, so if we had Wi-Fi in our warehouse, we could post to the cloud. Otherwise, we need radio to send our data to the office, which surely has Wi-Fi. So Wi-Fi is definitely one of the options if we have Wi-Fi access from the warehouse. Otherwise, we're going to have to send the data to the office building, combine it, if any, with any other data from the office, and then post it to the cloud using Wi-Fi. Okay, so what do we need? An MCU, of course. The Arduino UNO. So we're going to use this guy as our receiver, RX. Okay, we're going to receive data from RF radios. So we need the MCU to receive data, and of course we're going to need an MCU to send the data, which could be an UNO, but we're actually going to use a different one to transmit. This is going to be our sender or our transmitter. Okay, so this transmitter this MCU is going to be the one that actually has the sensors connected to it. So temperature, humidity, UV, and dust connected to the sender, and MQs for local air quality in the office connected to the receiver. Okay, we're going to skip over the MQs in this lesson, and we're going to go straight to adding the RF modules. So the RF modules, there needs to be one for the sender and one for the receiver. So we're going to collect data in the warehouse and send it via RF to our receiver. Okay, and as we mentioned, there's the second option, which is Wi-Fi. This only works. You can only post data from Wi-Fi if you have Wi-Fi access. So most warehouses don't have Wi-Fi access, not that I know of anyway. But, well, agricultural warehouse. And when we study Wi-Fi, we're going to look at the Esp8266 module for Wi-Fi. And we're going to look at the NRF24 for RF radios. Okay, so these are the two guys we're going to look at. Let's go ahead and see what they look like and how to connect them. Okay, so let's look at some of the different options we have for long distance or for short distance communication. So here we have a Wi-Fi module. This is the Esp8266. That's the Esp01 module. And over here we have some traditional or some, well, hobby grade RF modules. They work at 433 megahertz, and these are the antennas. So you can see that they're pretty small, but then again, you feed them very low power, so they don't have a long distance or a long range. We're basically talking about 10 centimeters, and that's about it. So we could use them for the car that we used in that car kit video, but it's not going to make it to the office. Okay, so as I mentioned, this is the ESP module, and it's got the pins over here on the side, and they look very similar to the NRF, so let's not get those confused. But this is the Wi-Fi part. Remember, the Esp8266 will work if we can post data to the cloud if we have Wi-Fi access, which is usually not present in the warehouse. So we're going to have to send the data first via RF, and then the Esp module is going to post it to the cloud. Okay, so let's move this guy over here. Let's look at the NRF modules. So we have two different types here actually. We've got one of these radio frequency long range, which is this long module, and these are the regular NRFs. So let's take a look at these first. So we got two right here, and they go about 100 meters. So distance we can cover is 100 meters. But this guy, as you can see, has an onboard antenna, and you can feed a lot more power to the module itself, and therefore it could go ahead and take advantage of this very big antenna that it can use to send data up to about 1 kilometer or so. So there's a big difference. In the regular NRF, the antenna is built onto the module, but in this one, it is actually an external antenna. So we're going to look at the pinout in a little bit more detail a little bit later on, but basically here it is on the long range one. We're not going to be using the long range one for this video because we only need to go about 50 meters. So, but I did want to mention the fact that there are those two options. So the modules are quite different. Obviously, it needs to receive more power so that it could transmit over a longer distance. And 1 kilometer is about as far as it goes. And these are the ones that we're actually going to be using. So we need one for the warehouse and one for the building, okay, which is actually going to be a room in this case. And then we're going to post to the cloud with the Wi-Fi module. All right, so that's what we're going to be using. Okay, so let's go ahead and wire things up. So I'm sure you've already looked at the pinout. You probably Googled for it. So let's get started with the NRF module. So here it is, and we need to connect jumper cables to this. There are adapters for it because it uses the SPI connection protocol or communications protocol, but this is what each pin turns out to be. So if you don't have an adapter, you can just connect jumper cables to it. Keep in mind there's a top view and a bottom view, so don't get them confused. It's very easy because you obviously have to connect them from the bottom. So in this case, I always keep in mind that VCC is straight across from ground and that MISO is straight across from IRQ. So we're going to get these plugged in according to the connection. It's kind of weird. Some of these jumpers, the plastic molding part on it is a little bit thicker on ones than others, and the pins are pretty close together, so sometimes you have to wiggle them into place, and sometimes you have to make sure that they're facing or that they're put in the correct orientation. Otherwise, one of the jumpers will actually get in the way of the other, and you won't be able to wire them in. So just try to wire things carefully so as to not damage either the pins or the actual jumper cable itself. There's nothing worse than trying to debug a problem with a module and it turns out to be a broken cable on the inside. Okay, one of the things you can do to avoid that is to use a continuity tester in the end to make sure that the pins on the module on the top side have continuity with the leads on the jumpers. Okay, so you start on one side and you work through pins in the through the module. Obviously, don't start in the middle of the module; it'll make things harder. Also, I try to use color coding, as I've mentioned many times before, just because it makes things easier when you're trying to check connections, and especially on this board or this module that doesn't have the labels on the board itself. As you can see, the NRF, the long range one, did have the connections on it, their actual labels on it, but this one does not. So, okay, I'm almost done here. Got a few more jumpers. There we go. Okay, and we're set. So, okay, Now, if you have the continuity tester, you could go ahead and do that right now. I've already tested these from before, so let's go ahead and plug these in. Now remember, this is a module that takes 3.3 volts, so you don't want to stick this into the 5 volt. Yes, there are a lot of reports that it takes at 5 volts, but you don't want to be the exception. Okay, so there's my ground cable. I always try to use green or black for ground. And there are, as you can see, the CSN and the CE cables on 7 and 8, I believe. And those are the ones that we'll define in code. And then the other ones that are specific to the SPI are the MISO, MOSI, and SCK. So that's MISO stands for master in, slave out, and MOSI stands for master out, slave in, and the SCK stands for system clock. Okay, so once that's in, make sure that all the jumpers are all the way in, and let's go ahead and wire the receiver. We're going to use a nano, remember, so we're going to have to use a breadboard in order to wire the receiver. Alright, so I'm going to skip through that and see you in the next one. Okay, so this is what it looks like. So we have the nano on a breadboard this time because we've added DHT11, whose data pin is connected, by the way, to pin number 6 on the nano, which is the sender. So let's look at some code. Now remember, this is what we have. The UNO is going to be receiving and the nano is going to be sending. So the sender is the one that has the DHT11 for sensing the data. And both of them have an NRF radio module, the nano to send and the UNO to receive. So okay, basically the includes the SPI library and the 2 NRF libraries which are required, as well as the DHT for sensing. We declare some a type, the pin number 6 for the sensor. This is for the NRF radio, the CE and the CSN, pins 7 and 8. Then we define a address, which is going to be used by the radio to communicate through. The DHT object, a structure package, which is interesting. It's basically a variable with other variables inside. It's used for complex data or mixed type data. And then we define a type def for it and create an instance of it called data. And then we define the radio object called radio. And then the last 3 lines are for time management. So we're going to try to be sending and receiving data every second. So we are going to be looking at this code later, but basically the interval there for TX interval millis is equal to 1,000 milliseconds, which is a second. And that's what we're going to use to tell the radio to send data from the nano to the UNO every time that interval is basically reached. And we'll see how to use that in a little bit. It's a very useful pattern in programming in general. So, okay. So much for this part. Let's look at the setup. So in the setup, we initialize the serial monitor and the DHT sensor object as well as the radio object. We set a few parameters for them. And in the loop is where we run through this Millis stuff. So what we do is Millis is the time that has elapsed since the MCU started. So whenever it reaches line 50, it reads how much time has elapsed and it stores it in current, which makes sense. And then it tests. If current is subtracting the previous millis, which we'll see later, is greater than the interval of 1 second, then we will go ahead and execute line 52, which is send. And then it will reset previous millis to current millis. So it'll basically reset itself every time it reaches 1 second, but it will only do so after calling the send function. So we're sending every second. Now let's go ahead and look at the actual send function. So here it is. We basically read the data from the DHT sensor. We store it in our 2 variables. And we go ahead and radio.write to send this data from our nano to our UNO. We also print that on the serial monitor just to check. And a few more messages down the road. For further debugging, we're not going to be using that much debugging in this case. And if it didn't receive it, then TX failed. So it did not transmit. Okay, so remember, this is the transmit side. So this is the warehouse. So let's go ahead and take a look at the UNO, which is the receiving side over in the office building. So this is what the code looks like. A little bit simpler, the same libraries, SPI, NRFs, The defines for the radio are always needed, the slave address as well for radio communication, the structure package, and we look at the setup. Basically the same stuff, serial initialization and radio initialization. No DHT sensor, obviously. And in the loop, we're basically doing two things, getting data and showing the data. So in the getting data, we check if the radio is available, we read it, and if it does come in with new data, then we go ahead and set this Boolean new data to true. And then we call show data, right? So in show data, what we do is if new data is true, then we go ahead and print that to the serial monitor, and we reset new data to false, which means that this data has already been printed, has already been shown. We don't need to show it again. So the next time you check the radio, new data better be false, otherwise it's the same data. Alright, and there it is in the serial monitor, data received, temperature, and humidity. Great, so data transmission, I mean, it's pretty simple between NRF radios, and we will go ahead and look at more detail in the next couple of videos, but in the next video specifically, we will look at actually seeing the data on a screen, which is a lot more useful, right, in an LCD, and we will look at this code in more detail if you guys should need it. So don't forget to like, share, and subscribe, and hopefully I'll see you guys in the next video, because this is a very interesting project. See ya!